Okay, I guess we'll go ahead and get started here. Um, First of all, does anybody have any questions before I start on Chapter 5 material? Nobody? Then we'll go ahead and get started. I'm going to share the document to start out with, which is basically Chapter 5 review material. And I will send this out to everybody. But let me see if I got the right one. Yes, okay. All right, brief review of Chapter 5. And what we're going to be doing in Chapter 5 is dealing with probability distributions. And they're going to be discrete. Chapter 6 is when we're going to start doing continuous distributions. But for now, we're talking about discrete distributions where the random variable, we'll call it X, typically takes on a finite number of values. And there's a gap between the values. It doesn't take up every possible number on the number line. It just takes on selected values on the number line. Like in the case of the distribution that's on the screen there in this document, 0, 1, 2, 3, 4, 5, 6, or 7. And then there will be a corresponding probability. Remember, all probabilities have to be between 0 and 1. And they have to add up to 1. So a couple of things. This has to be quantitative data, which these numbers are. The X values have to be quantitative. And quantitative means we need to be able to calculate with them. And the probabilities have to add up to 1. That's what makes it a probability distribution. So as we can see here, if we look at the values that we've got for probability here, let me annotate. These probabilities add up to 1. So if we add those up, well, I've done it already, but it does add up to 1.000. Oh, I gotta hook up my Wacom tablet. And hang on a second while I make room for it. All right. So anyway, these add up to 1.00. So this makes this a probability distribution. And let me dump these drawings. Okay, just put 1.00 down here. All right, so the one thing the first thing we're going to have to do with a probability distribution that's given to us, and by the way, you may be asked to calculate some probabilities in the homework or quiz, or fill in a table, but typically on a test, you're going to have to start with finding probabilities for a given probability distribution. You'll have to add up the probabilities to make sure they are equal to 1 and then find probabilities. For example, if we wanted to find the probability that a randomly selected value of X is 2 or 3, that means, and these, by the way, are disjoint. They can't happen at the same time. If I pick a random variable X value, I can't pick a 2 and have it be a 3 at the same time. So this is disjoint. So when we do OR probabilities, like we did in chapter 4, when we do OR probabilities, we're going to add the probabilities for the possible values of X in the probability statement. Okay, so our probability statement is, what's the probability that X is 2 or 3? So all we're interested in is the 2 or the 3, and then we have to add up the probabilities to get 0.261 plus 0.290, which turns out to be 0.551. And then going back to chapter 4, when we talked about the probabilities of at least and at most, these are going to crop up as well. So at least means that number or more. At most means that number or less. So you still have to remember these from chapter 4. What does at least mean? What does at most mean? So basically, probability of 6 or more is 6 or 7. Those are the only values of X that are 6 or more. So what are we going to do? We're going to now look at 6 and 7. And it's OR, so we're going to be adding these two probabilities up, and we'll get that 0.019. Okay, questions so far? All right, then one for at least, or at least 1. Well, at least 1 is important, because we will have probability distributions that start at 0, and we're interested in everything that's positive for X. So at least 1 means 1 or 2. Let me clear these drawings again here. At least 1 means 1 or 2 or 3 or 4 or 5 or 6 or 7. And to find that probability, we would add up all of these probabilities, and that would be our answer. But it's easier to add, instead of adding up every one of the probabilities except for the one up here, it's easier. We could just look at this and subtract it from 1. So the probability of at least 1 is 1 minus the probability of 0, which in this case, 1 minus 0.028, which turns out to be 0.972. Okay? Then if we look at probability of at most 2, that's 2 or less. So that means the probability of 0 or 1 or 2, which means we're going to add up those, or we're looking at only those values of X. We're going to add up the probabilities for those. And that gives us 0.028 plus 0.131 plus 0.261, which ends up being 0.420. So let me ask this. What is the probability of me randomly picking a random variable X value and finding it to be an even number? What's the probability that X is even? Which probabilities am I going to be looking at? Well, is 0 even? Yes. So is 2, so is 4, so is 6. So the probability that X is even is equal to 0.028 plus 0.261 plus 0.194 plus 0.017, which is going to be 9, 13, 20, 4, 10, 19, 20, 2, 4, 5. 0.500, is that correct? Anybody want to confirm that for me? That can't be right. Sorry, that's wrong. It has to be wrong. Okay, 2, 3, was it 0.50? I think it was, yeah, 0.50. It was right. Okay, so are there any questions on how to find probabilities using a probability distribution? Also, how to find out if it is a probability distribution to start with.
How do we find if it's a probability distribution?
All of the probabilities have to add up to 1.
Okay.
Okay.
Thank you.
And the X values are quantitative values, which
What is
most
that?
of them are going to be for our purposes.
Okay.
Okay. Are we good on
Thank
this
you.
then? All right.
Yes.
Let's move on. Let me dump this here. Clear all drawings. Let me stop this. And all right, now the next couple of things are really, really important. You're going to have to know how to do this. And we're going to be using our calculator to do it. But first, I'm going to explain how we would do it by hand. But you're going to be using your calculator. So, but explaining it, how it's done by hand, at least you'll see what's happening here, okay? Then when you use the calculator, you'll understand what's behind the operations on the calculator. All right. So to find the mean of a random variable, and I'm using the, I'm using the notation of the Greek letter mu for the mean and the Greek letter sigma for the standard deviation, because we're treating a random variable as a population, okay? So we don't use X bar here. We don't use S here. It's going to be mu and sigma, okay? So the mean is also called the expected value. So anytime you see the word expected or expectation, that means you're going to be finding a mean. You're going to be dealing with the mean. So here are the steps for finding the mean. Multiply each random variable value, by the probability. Okay. Then add these products. or the probability for the distribution that we're dealing with here, you would take, let me just move down. Can I move down? No, I've got to clear this. So to find the mean, I got to stop annotating too. To find the mean, I'm going to then multiply those two together, that, 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 and that. And then I'm going to add up the products. I'll come up with a total of this 0 times 0.028, 1 times 0.131, and so on, all the way down to 7 times 0.002. And I get, well, we'll see what we're going to get, because we're going to do it in the calculator. Okay. So that's how we find the mean. Take each random variable value, multiply it times its probability, and then add all of those up. Add those products up. All right, let's look at the standard deviation. Well, before we look at the standard deviation, let me just discuss what's happening when we find the mean. If we wanted to find the mean of just the x values, we would add up the x values and divide by 1, 2, 3, 4, 5, 6. There are 8 numbers here. We would add all these up and divide by 8 to get the mean of the x's. What we're doing when we find the mean is we're weighting each x by the probability, so that the one with the highest probability, like this 3 right here, is going to have more weight than any of the others. Okay? And if we look at it from the perspective of just finding the mean of the x's, we're weighting all those x's equally. We're calling each one of those having a weight of 1, 0 times 1, plus 1 times 1, plus 2 times 1, and so on. We give them equal weight, and then when we find the mean, we basically find the average of the x's. So when we approach it from a random variable perspective and assign probabilities as weights to the different x's, then we are going to we're going to find what is called the expected value, and that's the process we're going to use to do it. Okay, so basically it's just adding up weighted values of the random variable, but the weights are the probabilities. And when we weight it, we multiply the random variable value times the probability. Okay, now I'm going to briefly discuss how we find the standard deviation. And let's make it really brief. You're not going to have to do this. Okay? The steps are here, but we're not going to be finding the standard deviation of a set of data using this process right here. Basically, what we're doing when we find the standard deviation of these random variable values of x, we're going to subtract each one from the mean. We're going to square those. We're going to divide by the number of values. Then we're going to take the square root of that, and that's going to be the standard deviation. So we're not going to do this by hand. I invite you, though, when you're reading this document, to step through this and on paper see how it works. Okay? But what we're going to do is use the calculator to find both the mean and the standard deviation. So we're going to be finding the mean, and finding the standard deviation using the TI 83 and 84, or 84. Okay. And for this particular problem, I've got the windows from the calculator, but we're going to go ahead and step through this on the calculator. So if you've got your calculator handy, step through this with me. And I'm going to clear these drawings. I'm going to stop this. And I am going to bring this back up. And I'll tell you what, let's, if you want, I'll tell you what, let's write all of these down. I'm going to share the calculator. Oops, where is my calculator? All right, come back and start this over again. Share the calculator. All right. So the first thing I need to do is put the data into lists. I'm going to put the X's in list 1 and the probabilities in list 2. So I'm going to go to stat, enter. Okay. I'm going to clear out all of this stuff from my lists. I'm going to go up to, come on. I'm going to restart my calculator because it is acting squirrely. So let me quit out of here and open it back up. Okay, so. All right, here we go. We're going to go back and look at this again. We're going to put the X values into list 1. We're going to put the probability values into list 2. Okay, so I'll tell you what, why don't you take a moment and write all of these numbers down so that you've got them handy. So when we put them into the calculator, you don't have to rely on me telling you what the numbers are. Okay, so take a moment and write these down. And then I'm going to share the calculator and we'll step through this process. Okay, let's get this camera right now. Oops. Yes. 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 RG. No. Oh, yes. Kaylin is. No, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. All right, I'm missing one person here. Shauna's not here. Kaya is not here. William, Josiah is not here. There we go. All right. Okay, everybody got it written down, I assume. So let's go in and share the calculator. All right, so here we're going to go in and I go to stat and enter to get to here. I'm going to clear, go up to L1, hit clear and enter. Go over to L2, hit clear and enter. Because I'm going to put the X's in here and we're going to be 0 through 0, 1, 2, 3, 4, 5, 6, 7. And then go over to list 2 and I'm going to put in 0.028, 0.131, 0.261, 0.290, 0.194, 0.077, 0.017, and finally 0.002. Okay. And don't be confused by the fact that L1 of 1 right here is equal to the 0. Ignore this part right here when you're dealing with these situations right here. And just the first element 0 and then 1 and then 2 and so on. Okay? Because we're not worried about which element in our list. We're not going to identify the elements in the list by number or by designation. We're going to do it by the actual number. Okay, so 0, we're going to be doing 0 times 0.028, 1 times 0.131, and so on, all the way up to 7 times 0.002. But we're not actually doing it. The calculator is going to be doing it for us. So once this information is in our 2 lists, X is in list 1, probabilities in list 2, I'm going to get out of here, second mode. And now it's important that you know where to go to get this. It's important that you know what we're doing and then where to go to do it. So what we're doing is we're going to run a function that we've already run in the past called one-var stats. And if you recall, it's stat, right arrow to calc, and number 1 is one-var stats, or just hit enter. Now, if you have stat wizards on, this is what you're going to see. We have L1 already in list, but list is going to be L1. And now the frequency list is going to be our probabilities. So that was in list 2, so second 2. So for finding the mean and standard deviation of a probability distribution, we need to make sure that we're using both list 1, the X values, and list 2, the probabilities. And then we'll go down to calculate and hit enter. And now we've got our results. 2.8, and why they can't manage to put a mu in here, I don't know. But for probability distributions, the mean of the probability distribution is the X bar value, okay? That's where it's putting the mean. The standard deviation of the probability distribution is sigma X, okay? So now we know we're going to have 2.8 and 1 point. We're going to, I'll point this out now and I'll reiterate it later. For a random variable, the mean of a random variable, standard deviation of a random variable, these are parameters of the random variable, because remember, we're treating them like populations. These are parameters. The parameters will have 1 decimal place more than the actual random variable values. The random variable values are whole numbers, so there's no decimal places. So our parameters for that random variable is going to have 1 decimal place. So 2.8 is our mean for this random variable, and 1.3 rounded to 1 decimal place, 1.3 is the standard deviation of the random variable. So 2.8 and 1.3. Questions on that? So just to step through it one more time, to find for a given random variable distribution, probability distribution, with x's and probabilities, you're going to put the x's in list 1, the probabilities in list 2. Remember, that's under stat, enter to get to the list. Then you're going to run 1var stats, which is stat, right arrow to calc, enter, and then you will, for the list, you're going to put L1. For the frequency list, you're going to put L2. If you have stat wizards on, it'll indicate those things. But what I'm going to do here is, let's come back here and I'm going to set my mode to, I'm going to have stat wizards turned off. Right now it's on. I'm going to turn it off. Enter. And then get out of there. And now I'm going to do stat, right arrow to calc, enter. Now we only see 1var stats. We're going to have to type in second 1 for L1, and then the comma, which is above the number 7, and then second 2 for L2, and then hit enter, and we get the same result. Okay? All right. Questions on how to find the mean standard deviation for a probability distribution? Should be straightforward. Did you have a question? I think you've got your mute, you're muted.
I'm not muted. I'm trying to turn up the microphone. Can you hear me now?
Can't hear you. What? Oops, you're muted again.
Okay. Now I'm having trouble with my speaker. I'm trying to use the earphones and the microphone, but it's working. Can you hear me now?
Okay, try it one more time.
Now?
I can, you're breaking up, but go ahead and try it again. Say again.
Okay. I have a TI-83, so I wasn't getting the same screen as you did.
Yours is a TI-83.
83 plus.
It's a TI-83 plus.
Yes.
You
sir.
should be able to, well, you're not going to have stat wizards.
Right.
Okay, stat wizards is not on the TI-83 plus. It's only on a TI-84 plus. So you'll do it like I just did it this way. You don't have, you're not going to have to change anything in your mode. you're just going to put the data in, the X's in list 1 and the probabilities in list 2, and then run 1 var stats, and you'll have to type in the L1 comma L2.
Okay.
Okay?
Thank you.
Is that okay? Okay, so, all right, let me get away from the calculator. Do you need the calculator, Deborah? Or, I'm sorry. Yeah. Where are we here? Oh, I lost something. Deborah, you're okay now? Okay, good. All right, I'm going to stop sharing. Actually, I'm going to go back to the document. So what we had 2.8 and 1.3, as I recall. Where's mine? Gotta share again. Okay. So our mean turns out to be 2.8. And let me go ahead and annotate. So our mean was 2.8 and our standard deviation was 1.3, rounded to 2 decimal places. So now, let me stop sharing here. Annotate, clear. Now stop sharing, close this up. All right, now, oh, I had both of the input screens showing here. So this is, Deborah, this is what you're going to see. Okay, so now let's consider this range rule of thumb, which I believe you had in Math 1530 back in chapter 3. And also possibly in chapter 4, but the range rule of thumb basically is a rule to determine what values of the random variable are extreme, which means they're far away from the mean. So the rule of thumb for being far away from the mean is more than 2 standard deviations away from the mean, which means to calculate what the minimum usual value is, we would subtract 2 times the standard deviation from the mean for that's the minimum usual value. So if it was exactly equal to a random variable value was exactly equal to that, then it would be usual. But if it is more than 2 standard deviations away from the mean in the subtraction direction to the left on the number line, it would be considered to be unusual. And then on the positive side, we would add 2 standard deviations to the mean to get the maximum usual value. So any number equal to mu plus 2 sigma is going to be usual, but anything bigger than mu plus 2 sigma is going to be unusual. And any number that is between those two, the maximum usual and the minimum usual, are going to be usual. So if we looked at it on the number line, it would look like this. And let's see if I can do it here. Here's the number line. Here's the mean. Here is the mean minus 2 times the standard deviation. Here is the mean plus 2 times the standard deviation. And everything from here over to here would be usual. And anything out this way would be unusual. And anything out this way would be unusual. Okay, so everybody okay with this definition of usual and unusual using the range rule of thumb? So we need to determine what values of X are usual, or I'm sorry, we want to know which values of X are unusual. So when we do this, the minimum usual value, we take the 2.8, which is the mean, minus, 2.6. That's 2 times. There's a mistake in here. That's 2 times there, and it's 2 times here. But these numbers are right. So 2.8 minus 2.6 is 0.2. So here's the minimum usual value for our random variable. So this is 0.2. And the maximum usual value is 5.4. So this is 5.4. So now we need to figure out what values of X are smaller than 0.2. Okay. Well, X is 0, 1, 2, 3, 4, 5, 6, or 7. What values are smaller than 0.2? Anybody? Nobody? Well,
0.
0 is. 1 is between these two numbers. 2 is, 3 is, 4 is, 5 is. But what about bigger than this? So 6 and 7 are unusual. Unusually large. 0 is unusually small. In other words, if we randomly pick a value of X, it would be unusual for us to end up with a 0 or a 6 or a 7. Anything else would be considered, this is what we would expect to see. Anywhere between 0.2 and 0.54, we would expect to see those numbers. But if we get a 0 or a 6 or a 7, we would not expect to see those numbers. Those are numbers that are unusual. So you need to be able to make that distinction. You need to be able to find the minimum usual value, find the maximum usual value, and determine what values of the random variable are unusual. And the reason we're doing this is you're going to see when we get into chapter 7 and beyond, that we're looking for unusual values to determine if an assumption, if we're going to keep an assumption that we make or throw it out. Okay. And by the way, just as a little aside here, statistics is all about information, having information to make decisions. Statistics is used to help to make decisions. And if you make an assumption about a random variable and you collect data and your data does not reflect what that assumption is, then you're going to question your assumption. Okay, so in essence, from chapter 7 on, that's what we're doing. That's what we're going to be doing. Okay, so we'll have random variables to work with. We'll be doing some calculations, and a lot of it's going to be done on the calculator, and the results of those calculations are going to tell us we'll have rules for comparing those results to what we would expect and what we would not expect. And if we we get something we don't expect, we're going to question our assumption that all those calculations were based on. Okay. All right, so let me clear this up and get rid of this. I gotta move my screen. Okay. Now, we just looked and found we had a definition for using the range rule of thumb. We had a definition for usual and unusual values. Now, when you see the words unlikely, unusual, unusually high, or unusually low, then they are kind of mean the same thing. A random variable value is unusually high if the probability of at least that value occurring is less than or equal to 0.05, which is an arbitrary number, but it's basically a small probability. And we could make it even smaller. We could use 0.01 or 0.0025 or something like that, but a small probability. And we find, actually, let's go back to the original problem, which was our probability distribution here. So, and let me go back and annotate this. Oops, now we're going to do that. Okay, we said this was unusual, right? And we said that these were unusual. Okay. So we would say that 0 is unusually low, because the probability of 0 or below, and there are none below, but the probability of 0 and below, which don't exist, is less than 0.05. Okay, so we would say that 0 is unusually low. Then if we looked at 6, then we would say, all right, it's unusual by our range rule of thumb, but the probability of 6 or above is what, 0.019. So because of that, 6 would be unusually high. Because 0.019 is less than 0.05, or whatever number we've used in that position, okay? So for unusually low, we would take all the to determine if a random variable value is unusually low, we would take all the probabilities for it and every number below it, add them up, and if it's less than that 0.05, we would say that number, that random variable value is unusually low. And for a value like 6 here, that we would look at to determine if it's unusually high, we would look at its probability and all the probabilities above it, add those up, and if that total is less than 0.05, we would say that 6 in this case is unusually high. If we wanted to look at 7 and determine if it's unusually low or unusually high, well, it's 0.002, and there aren't any numbers above it, so this probability happens to be less than 0.05, so it also is unusually high. Okay, that's the terminology that is used quite a bit. I'm not sure how I'd have to go look at the homework examples and see if they focus on that You may see a question or two on that, but I would spend a minute or two trying to figure out, or trying to understand anyway, what unusually high means and what unusually low means, okay? And just look at the definition that's given here in the notes here. Okay, so let me clear this. Questions on this? I know it's new. It's maybe a little fuzzy in your mind right now, but spend a little bit of time reading that definition again, and try to go back to this this probability distribution here and see if you understand in this probability distribution what those definitions are telling you. Okay. And by the way, I'm recording this, and I'll give you guys a link to it later on, so you can go back and look at this if you want. All right, so let me clear this. Dump this. And unusually low, range of thumb, unusually low, unusually high. Okay. That is everything that you're going to need. I think we've covered everything you're going to need for the first chapter 5 homework. Okay. Now I'm going to start talking about the a specific probability distribution called the binomial. And this one's really important, and you'll see a lot of problems on it on the test, because the test is only going to cover 2 chapters this next time. By the way, it's probably only a couple weeks away because we only have 4 homeworks in between. Anyway, you'll see lots of problems on the binomial. So you're going to have to understand what binomial distribution is, what makes it a binomial distribution, and how to find binomial probabilities and use them. So let's go ahead and let me move this out of the way. Come over here and, okay, binomial random variables. Definition. We're going to have a finite number of trials. Okay, so if we have a finite number of trials, in other words, we're going to randomly, we're going to conduct an experiment, and in that experiment, we're going to conduct a finite number of trials. We're going to run this experiment a finite number of times. And each time there's going to be exactly 2 outcomes. And we'll call those outcomes success and failure. Why do I have, this is all screwed up over here too. Okay, so finite number of trials, each has exactly 2 outcomes. We'll call them success or failure. Then the second thing for a binomial random variable is there is a probability of success that is constant for each trial. Like if I flip a fair coin. If I flip a fair coin a finite number of times, say 10 times, and how many outcomes from a toss of a coin? It's either going to be heads or tails. There's only 2 outcomes. And we'll call a heads a success. We'll call a tail a failure. Okay? The probability of success is they're equally likely to happen. So the probability is 1/2 or 0.5. So the probability of success on each toss of the coin is going to be 0.5. Probability of failure is also 0.5. And then a random variable value, this is important too. Random variable value takes on all possible values, all possible numbers of successes. Okay? If I toss a coin 10 times, I can have no successes. So 0 is a possible value of the number of heads. I can have no heads. I can also have 1 head, or 2 heads, or 3, or 4, or 5, or 6, or 7, or 8, or 9. And I can have 10 heads. All of them are successes, no failures. Okay? Now, how do we find the probability? Probability, there's a formula for the probability, but we're not going to worry about this formula. Okay? This is it. It wraps around down here. Okay, that's the formula. And we use a combination in that formula. Okay, so, and I'll tell you how to, we're going to find probability, binomial probabilities on the calculator. So you don't have to remember this, this formula right here. So let's go back to another example that gives us this table right here, probability distribution for number of successes. We're going to have a multiple choice test, okay? Each test has, the test has 5 questions. So we're going to treat these as, let me clear this out here. We're going to treat these 5 questions, and they can either get the question correct or not, okay? So these are trials. All right, now there's 4 choices. They're multiple choice. Each question, let's just look at the structure of a single question. The single question has 4 possible answers. And if we randomly select an answer, in other words, we're guessing on each question, the probability of success or getting it right is what? How many possible choices can I make? There's 4 choices to make. Those are basically simple, simple events, like from chapter 4. I got 4 possible choices, 4 simple events, but only one of those matches correct. So the probability of success is 1 divided by 4, or 0.25. Okay. So the probability, let me see here. Probability of success is, remember that's the second one here. Actually, this should be B, and that should be C. But anyway, 5 trials, probability of success on every question, because we're going to guess on every question, is 0.25. Okay. And how many possible correct answers can I have if I do all 5 questions? I can miss them all, which says 0. I can miss only 3 of them and get 1 correct. I can miss 2 of them and I can miss 4 of them and get 1 correct. I can miss 3 of them and get 2 correct. Miss 2 of them and get 3, miss 1 of them and get 4 correct, or I could get them all 5 correct. So it's good to know what the possible values for the number of successes is. So remember, it starts at 0 and goes all the way up to the number of trials. Okay? Binomial random variable starts at 0 and goes all the way up to the number of trials. All right, so got these probabilities in here. You might want to take a moment and write these down, 0 through 5 here, 0.237, 0.396, etc. I'll give you about 15 seconds to do that. Okay. Now what I'm going to do is go to the calculator and I'm going to show you how to calculate binomial probabilities. So you're going to need to know how to do this. Okay, let me clear this out so I can switch over to the calculator. And I'm going to go share the calculator. Oops. Oh, I'm going to quit. Don't do that. Okay, share the calculator. I'm going to get away from there. All right, ready? Here are the steps. Finding binomial probabilities on the calculator. We're going to do second vars. And we get a list of all kinds of probability functions. We're going to arrow down to binom PDF. Okay, not CDF, but PDF. Binom, think of it, binomial probability distribution function, PDF. Okay, that's what we want. So we're going to do second vars, go down to binom PDF, hit enter, and I don't have Stat Wizards on, and I'll show you what it looks like when Stat Wizards are on, but here I have Stat Wizards off. We're going to put in 3 things. You have to know what 3 things we're putting in and what order we're putting them in. So our problem was 5 multiple choice questions with a probability of success on each one of 0.25, okay? So I'm going to put in first the number of trials. The number of trials was 5, so I'm going to put in a 5, and then a comma, which is above the 7. Then I'm going to put in the probability of success, which was 1/4 or 0.25. And you could just put in 1 divided by 4 right there and let the calculator handle the division for you. I could have done, oops, I just did that. Second vars, binom PDF. Uh, 5, comma. I could have done this. Could have put in 1/4, okay? Comma. Then I'm going to put in the number of successes. Let's start out with 0. That's the first value of X. And then I close the parentheses. So I've got N, and by the way, N is usually the typical designation for number of successes. So N, and then P is 0.25 or 1/4. And then X is the number of successes. So NPX. Okay, NPX. Trials, probability, random variable value. And then you don't have to put this closing parenthesis on it because the calculator is tolerant in that respect. And I'm going to hit enter. And by the way, what was the probability for that first one, for a 0? Anybody want to tell me what that was? It's covered up on my screen, so. Was it 0.257? Okay. 237, 0.237. And then we'd round that to 3 decimal places if that's what we wanted, okay? Now I can do this for all the probabilities. I can do it for, basically do binom PDF for 1 and then 2. All I have to change is this number right here. Is that 0 to a 1 or a 2 or a 3 and so on. Now, what I can do though is rather than go hunt up Binom PDF again and put this type the stuff in, I can do this. You might want to take note of this. I can do second enter, which you on a TI-83 plus, that's what you would have to do to get this back again. And then use the arrow keys to change that X to a 1 and hit enter. And I get 0.396. Okay. Now, if you, I think if you have a TI-84 plus, let me know if you can't, but you should be able to just arrow up to the previous statement. You can't do this on the TI-83 plus, but if you have a TI-84 plus, you can use the up arrow to get back up to that and hit enter, and it brings it up. And we'll change that to 2 and hit enter. And we'll do that for all the numbers. Bring it to 3. Enter. Might as well just go ahead and do this. Change it to 4. Enter. Oops. To 5. Enter. To 6. Enter. And oh, there was only 5, weren't there? Notice when you put in a number that doesn't, that X can't be, you end up with a 0. Okay, so let me get, oh, one more thing. Everybody okay with finding a binomial probability now? You got to remember where to go to get it. You're going to do second vars, arrow down to Binom PDF, hit enter, type in N, the number of trials, comma, P, the number of successes, or number of the probability of success, comma, and X, the number of successes. Then I'm also going to show you that if you wanted to do this, you wanted to know all of the probabilities, you can do this. Instead, if we've got our number of success, number of trials and probability of success, if we just stop right there and don't put in the comma and the number of successes, so we've only got 2 things in there: the number of trials and the probability of success. Hit enter. Notice what we get. We get all of the probabilities at once. But unless you need them all at once, just go and do them one at a time for the ones you need. Otherwise, it's without creating this, putting these in a list and then looking at the list, it's difficult to decide which one you're looking at. Okay. So let me clear that. Now, one other thing, well, let me go back and look at, do second vars again, go down to Binom PDF. Oh, I'm sorry, I didn't want to do that. Second, quit. Let's do this. I'm going to change my mode back. So if you're not looking at, if you have StatWizards on, oh, come on. If you have StatWizards on, this is what you're going to end up seeing. Hit second mode after you change it to on, and then do second vars down to Binom PDF. Now you see this. It's going to specifically ask you for it's going to ask you for the 3 things. So in this case, we would want, we would put in 5 trials and 0.25 probability of success. And we would put in the number of successes. If we left this blank, we would get them all. But let's say I'm going to put in the last one. I want the probability of success of 5 successes. And then we paste it. And notice it puts it back into the Binom PDF function, which is what you end up doing without StatWizards on. You end up having to create this yourself, okay? And then we get our probability. So everything that I've covered there is basically, so far we've talked about what is a binomial random variable, what makes a binomial random variable, and now we know how to find binomial probabilities, okay? So let's, I'm gonna close this, come back to the document, and the steps, by the way, for using the calculator to find binomial probabilities are in here. Now, finding the mean of a binomial random variable. Before, we just had a plain old random variable where we had the random variable values and we had their probabilities. To find the mean, we multiplied each binomial value by its probability and then added them all up and we got our mean. And then we also could have done this on the calculator using 1-bar stats, okay, for the mean and the standard deviation. We have formulas for binomial though. We don't have to do 1-bar stats for binomial random variables. All we need to know is how many trials there are, what's the probability of success, and for standard deviation, we also need to know what's the probability of failure. And let's just take a peek here then. I'm going to annotate because it's easier to point things out. Okay, the formula for the mean is equal to the number of trials times the probability of success. And by the way, that formulas and tables handout that is available in the content on the D2L homepage, these are there. And when you're taking a test, or even when you're doing the homework or quiz, it would be a good idea to have that printed out so you can refer to it and not have to look it up, okay? So I would definitely print at least the formulas and the formulas part of that, just so you have that handy when you're doing work. So anyway, N times P. For our problem, we had 5 trials, 5 multiple choice questions, and we have a probability of success on each one of those of 0.25. So when we multiply those together, we end up getting 1.25 as the mean for the random variable, this binomial random variable. Okay, so it's pretty straightforward finding the mean of a binomial. Same thing for standard deviation. Now it's, rather than you doing 1-bar stats, the standard deviation is just the square root, and you have to remember that square root because a lot of people leave it off. If you leave that square root off, you end up getting the variance rather than the standard deviation. But you're going to be needing the standard deviation, so you need to remember that square root. And under the square root symbol, you're going to have N again, number of trials, P, the probability of success, and Q. Q is the probability of failure. That's the typical designation for a binomial probability of failure. Q is nothing more than 1 minus P. Because you either have a success or a failure. Those two things are complements of each other. And so the probabilities have to add up to 1. If we got a probability of success of 0.25, 1 minus that is the probability of failure of 0.75. So we end up with 5 for N, 0.25 for P, and 0.75 for Q. And when we put that into the formula, we end up with 0.968. Okay, you'll need to remember those formulas, or at least know how to access them quickly when you're working in homework quiz or when you take the test. Okay. All right. Now, back to the range rule of thumb. Remember what the range rule of thumb was. And I need to clear this. Remember our range rule of thumb. The minimum usual value was mean minus 2 times the standard deviation. The maximum usual value was mean plus 2 times the standard deviation. Well, we're going to use those for binomial as well. So we're going to, here's our minimum usual value. Oh, come on. Minimum usual value, and our mean, oh, we didn't find the standard, did we find? Yeah, we got 9.968. And we're going to use, again, 1 decimal place. So the 1.3 was the mean, and the standard deviation turns out to be rounded to 1 decimal place is 1.0. So the mean minus 2 times the standard deviation, the minimum usual value is 1.3 minus 2 times 1 is negative 0.70. Now, the interesting thing here is we have no negative values for X. So if we end up finding a range rule of thumb value, minimum usual value that is less than the smallest X, we'll just use the smallest X, okay? Because there are no negative X's. And then for the maximum usual value, 1.3 plus 2 times 1 ends up being 3.3, which is not bigger than the biggest one. If it were bigger than 5, we would make this 5. So our 0 to 3.3 are going to be considered usual. And in unusual values, there would be ones that are less than 0, but there are none, or ones that are bigger than 3.3, and those are 4 and 5. So 4 and 5 are unusual. So if we ran this little experiment, if we took this test of 4 multiple choice questions and guessed on every one, it would be it would be unusual. I don't know if it's highly unusual or not. Let's go back and look at the probabilities, but hang on a second. I'll finish this thought first. It would be unusual for us to get 4 or 5 correct. And if we needed to get at least 3 correct, it would be a very small probability of getting all 3, or of getting 3 correct out of the 5. Or of passing. So let me clear this, and let's, 4 and 5 are the only unusual values. So let me get rid of this and come back to this and get rid of that. And okay, so the probability of at least 3, which is all passing, right? 3, 4, or 5, if 60% were passing, would be 0.088, 0.015, and 0.001. So that looks like 0.09. What do we got here? 0.094. Probability of us passing the test by guessing on 5 multiple choice questions with 4 options each is it's less than 10%. Okay. So anyway, we've got 0 to 3.3 would be the minimum, would be the usual values. 4 and 5 would be unusual. Okay. And I think I talked about if the minimum usual is less than the smallest x, we'll use the smallest x as the minimum usual. If the maximum usual is bigger than the largest x, then we'll use the largest x as the maximum usual. Okay. Now, special problem for binomial. A problem similar to this one. Consider a tour agency who books, oops, let me annotate here. Consider a tour agency who books paddle wheel singles cruises on the Mississippi River. There are 30 rooms on the boat. But historically, the probability that someone who makes a reservation actually showing up to pay for the ticket is 90%. So there's a small chance that anybody who books a ticket doesn't show up. So to try to make sure that they fill everything, they will possibly overbook. And in this case, try overbooking by 1. In other words, for 30 rooms, they'll take 31 reservations, thinking that most likely one of them is not going to show up. So they still fill all their rooms. Okay? And the problems like this are going to be, maybe these are vehicles, car rentals or something like that. They take reservations for more cars than they have, thinking that somebody's not going to show up, so they'll still fill all the cars. Or hotel rooms, or airline seats. They book more seats, more than they have, they book more people than they have seats, thinking that somebody's not going to show up, but they'll still fill their seats. So these are, I call these overbooking problems. And typically we'll overbook by 1. And so we just have to figure out in the problem, what are the trials? What's the probability of success? And then when it asks us for a probability, what is the value of x that we're finding the probability for? So we need to know what n is, the number of trials. We need to know what p is, the probability of success. And we need to know what x is, the number of successes. So let's look at this problem here. All right, they have 30 rooms, but they're going to take 31 reservations. My question to you is, this is probably the hardest part of these problems, is which of those two numbers is our number of trials? Remember what a trial has to have associated with it. It has to only have 2 possible outcomes. The 30 rooms are always there. They don't just disappear and appear. So there aren't 2 outcomes for a room. But the reservations, the outcomes for the reservation is the person who makes the reservation shows up or they don't. That's what makes the reservations, or the bookings, or whatever that we want to call them. That's what makes that a trial. So we have 31 trials here. I'm going to get rid of that. Here's our number of trials. So trials, I'm going to call it n. Okay. All right. Number of trials is 31. And we know that the probability that somebody shows up once they make a reservation is 90%. So this 90% is the probability. So we'll call this 90% P. And now, how about the number of successes? Here's the question that we're answering. What's the probability that they don't have enough seats or enough rooms? What's the probability they don't have enough rooms? When would they not have enough rooms? For what values of n would they not have enough rooms? Remember, n can go anywhere from, n is anywhere from 0 to 31. I'm sorry, n is 31. X is anywhere from 0 to 31. Okay? X is anywhere from 0 to 31. What value of X would mean that they don't have enough rooms? Well, if they have 30 people show up, do they have enough rooms? Yeah, they've got 30 rooms. If they have any number less than 30 showing up, they have enough rooms. It's only when the X is equal to n. When X is equal to n, they don't have enough rooms. And this is going to be the same on any of these booking problems. If X is equal to n, they don't have enough seats. They don't have enough rooms. They don't have enough vehicles, or whatever's the trials consist of, okay? So we know then that in this case, n is going to be 31, p is going to be 90, and x, x is going to be 31, okay? So what we're going to do then is to find out, it's a binomial probability. What's the binomial probability that the number of successes is X? I'm sorry, that the number of successes is 31. So we do the binomial PDF. With n is 31, p is 0.9, x is 31, and we get 0.0382. Okay. Now, typically there's another question that's asked along with this. And that question is, do they want this probability of not having enough rooms or seats or cars or whatever, do they want that probability to be large or small, and why? Remember, not having enough rooms is a bad thing because they've got to compensate the person who showed up and doesn't get a room. So this is a bad thing. So do you want the probability of a bad thing to be large or small? No, you want it to be small. And so if it's small, that means, you know, they've attempted to fill their rooms, and there's a small probability that they'll have one fewer rooms than they need, but they have filled the rooms, okay, so with a small probability that they won't have enough. So that's what they're looking for. They want this to be as small as possible. Now, what happens if they overbook by none? Would they, if this, and by the way, another rule of thumb here is if this is like less than 0.05, then they're good, okay? 0.05 is kind of like a standard maximum value for error, okay? So if this is less than 0.05, they would keep their overbooking like it is. But if this is extremely small, like very close to 0, that means that they have most likely will once in a while not fill their rooms. They might want to overbook by more to fill their rooms. As long as they can keep that probability of not having enough rooms small enough. Okay, so they want this to be small because it helps them keep, by overbooking, they keep their rooms as full as they can and don't frequently inconvenience anybody. And another question that might come up here is, what happens if the probability of success increases or decreases? If the probability of success increases, then so does, I'm sorry, probability, if the probability of success increases, let me clean this up a minute. Okay, let's just look at this probability of success. If this increases, so does this. They increase in the same increase and decrease together. Okay, if this increases, so does this. If this decreases, so does this. Okay, just keep that in mind, that if this goes up, this goes up. If this goes down, this goes down. All right, so if you don't mind, let's go look at some of the chapter, actually I'm gonna look at homework 5.2, okay? And let's look at a couple problems in 5.2. So that's what I'm gonna do, is make sure I've got, oops, hang on a second here. We're all going, just get rid of this, and look at this. It's still in it. Good. Oh, just crashed. Let's do this. Less than 30 seconds. All right. Assignments. 5.2. All right, let me come back and share. Stop sharing and come back and share the screen. All right, let me, I'm gonna skip that one, and what I really want to do is skip that one, skip that one, skip that one. Oops, wait a minute, what was that? Where are we here? I want to come back to number 12. Here we go. A shuttle company has a policy of overbooking because, based on past research, 92% of people who buy their tickets actually show up to ride the shuttle. their shuttles seat 19 passengers. If they sell 20 tickets, what's the probability there won't be enough? So this is just like the other problem we had. So basically, we need to determine then, we need to determine what is the number of trials and which is it going to be, the 19 seats or the 20 tickets? Remember, the tickets, they either show up or they don't. That's what makes this the number of trials. So that's N. And then the probability of showing up is 92%. So that's P. And we want to know what's the value of X that has a probability of not enough seats for the passengers. And what is X going to be equal to if there aren't enough seats in this case? X is going to be equal to N. And so, which in this case is going to be 20. All right, so probability of not enough seats will be, so let's go do this. We want N is 20, P is 0.92, and X is 20. So I'm going to go back over and show the calculator again. Oops. Clear this. Again, we're finding a binomial probability, and that, remember, is second bars, arrow down to binom PDF. Number of trials is 20. This is 0.92. And number of successes is also going to be 20. That's the only situation where they will not have enough seats. Paste, enter, enter, 0.1887 to 4 decimal places. 1887, let me back to share, 1887. So this is going to be 0.1887. Well, it's 3 decimal places, so 0.189. Okay, now the interpretation question. Do they want this number to be big or small? So this is saying that almost 20% of the time, they're going to inconvenience a customer. That's pretty big. One in 5 trips, they're going to inconvenience a customer. So they want this to be small. That way they can fill their seats or come close to filling their seats and not frequently inconvenience or regularly inconvenience customers. So it looks like A is the correct answer. They can decrease their profit, or I'm sorry, decrease their profit and regularly inconvenience their customers. No, I don't think A is right. I think C is right. They can increase their profit, but do not regularly inconvenience their customers. Okay. A is for people who don't want to stay in business. All right, so let's check our answer. All right, let me come back to 12. All right, a brand name has 50% recognition rate. Assume the owner of the brand wants to verify that rate by beginning with a small sample of 4 randomly selected consumers. Okay, so let's figure out, is this going to be a binomial situation here? They select 4 people. What's the probability that 3 or 4 of the selected customers or consumers recognize the brand name? Okay, so probability of recognizing the brand name. Do we have a number of trials? They're going to ask each of these 4 people the same question. So it looks like those 4 people are the trials. So here's the trials, 4. And what's the probability that 3 or 4 select the customers, that selected consumers recognize the brand name? Well, what's the probability on each question? At each time they ask that person a question or a person a question, it's a 50-50 chance that they're going to say they recognize it. So our probability of success is given to us as 0.5. So N is 4, P is 0.5. And then what's the number of successes we're looking at? 3 or 4. The question gives us the number of successes here. So we want the binom PDF of 3 and the binom PDF of 4. So if we go back and look at the calculator, let me just go up and steal that. And I'm going to change this to 4. And this is 0.50. And this is going to be 3. And then we're going to do it also for 4. So 0.25 is the probability for 3. And let's find it for 4. And 0.625. So the probability of 3 or 4 is 0.25 plus, oops, hit the right button here, plus 0.0625. So 0.3125 is the probability that 3 or 4 of the 4 people answer that they recognize the brand. So 0.3125. What are we gonna do here? Oh. 0.3125. Give our answer. Oops, incorrect. Oh, 3 decimal places, sorry. This is, if you don't look at this, you're liable to make a mistake. So we're gonna round this to 3. The 4th number is 5, which is 5 or more. So we're gonna make that round up to 3.3. All right, there we go. All right, 13, 14. Make sure that you know how to do these problems here. 15, comes out of here. Let's try this one as well, and then this will be it, okay? All right, business owner wants to know if it will be profitable to open a new coffee shop in a nearby town. In towns where the shop has been successful, the shop's name is recognizable to people 56% of the time. So again, it's recognizing the brand, basically. He surveys a random sample of 11 residents of the town. So he's going to ask 11 people if they recognize his coffee shop. And so we need to know what the number of trials is. And that is going to be the 11 residents. And they either recognize it or it don't, or they don't. So this is N. Do that. Yeah. Oops. So n is 11. And probability of recognizing it is 0.56. Find the probability that none, so the number of successes is 0. Okay. All right. So again, it's binomial. N is 11, P is 0.56, and X equals 0. So we're going to go 11.56, 0. So we're going to do this, change this to 11. I've got to insert another one, 0.56 and 0. Okay, that's extremely small, but it's in scientific notation. So you're going to see from here on out, if you already have seen it a couple times in homework and quizzes, but you're going to see probabilities that are in scientific notation. Okay, so let me just do this quickly. Annotate. Okay, so this is scientific notation. All right, so how do we change this to a decimal? We're going to look at, it's a negative exponent, so we're going to move the decimal point 4 places to the left. So this is going to go over 4 places. 1, 2, 3, 4, and we're going to have a 0, 0, 0, 1. We'll round it to 4, and that means that this 1 says this stays at a 1. So this is going to be 0.0001, or if it's 3 decimal places, we'll only have 0, 0, 0. Okay. All right, so let's share. Probability, 6 decimal places. What do I want here? 6 decimal places. 0.00120, okay? Yeah. So this is going to be for 6 decimal places. Oh, got to answer this too. Now, the probability that nobody recognizes it, do they want that to be big or small? Remember, nobody recognizing the brand name is a bad thing. So they don't want the probability of a bad thing to be large, they want it to be small. So it's either going to be B or D. If it is small, it means it's more likely that no one will recognize. No. Higher probabilities means higher likelihood. It means it is less likely no one recognizes it. So D is the correct answer here. Okay. They want that probability to be small. Okay. All right, I've kept you the full time talking about this, but we've covered everything that you should have everything you need from this to do the 5.1 homework and the 5.2 homework. Okay, so everything for the for chapter 5. All right, so I'll let you go. Thanks for hanging in there. I don't know who else is in. How many people are left? 6, 7, 2, 4, 6, 7. Wow, only one person dropped out. Very good. So have a good week. We'll see you next week.
You too. Thank you.
Right here.